Welcome back to the Network Architecture Design Series. I'm Ray. In this episode, we're focusing on a critical issue, network flapping. This case comes from a real-world network we introduced in Episode 1, so let's start with a quick recap.
Let's look at this network. This is a real-world network, and all the problems here are real. This network consists of a headquarters in New York and 3 data centers located in New Jersey, New York, and Dallas, along with many branch offices. In our last video, we identified 4 major problems in this network. One of the major problems is a network flapping issue. It happens between the New York headquarters and the New Jersey data center. This problem has never been resolved. Let's dive into this flapping issue.
Here's the information of the network flapping issue. There are 2 WAN routers on the site, New York headquarters and New Jersey data center, but currently only one router is active for this connection. The other sits idle. There is a direct link between New York headquarters and New Jersey data center. BFD and routing protocols EIGRP and BGP are enabled between the 2 sites. Engineers notice that BFD, EIGRP, and BGP are frequently flapping, but found no problem with the physical link and physical ports. The root cause remains unknown and the issue is not resolved. This raises a good question. Why traditional troubleshooting cannot fix this problem? And what can fix it? Traditional troubleshooting focuses on links, devices, and configurations. But what if the real problem is not links, devices, and configuration? What if the issue is actually in the network design? In that case, no matter how much you troubleshoot, you never fix the problem because you are looking in the wrong place. So we need to shift our mindset. Traditional engineers often focus on the question of how to fix it, how to configure it, how to test it. Architects often focus on the questions of what and why. What is flapping? Why is it happening? Once you have answered the questions of what and why, the solution usually becomes obvious. So, what exactly is flapping? Simply put, flapping means a network element is repeatedly changing state, up, down, up, down. It's not stable. Flapping is a network instability issue. In networking, flapping is often worse than a complete failure because it triggers constant recalculations across the entire fabric. Flapping, or network instability, can happen at different layers. At the physical layer, for example, a loose cable or a faulty SFP causing an interface to bounce. At the system layer, for example, CPU spikes, buffer congestion, or memory leaks causing unpredictable system instability. And flapping can also happen at the protocol layer. For example, BFD, OSPF, EIGRP, or BGP sessions constantly dropping and reestablishing.
Regarding the relationship between cause and effect, there is a philosophy that believes that every cause has its effect, and every effect has its cause. Therefore, by tracing back the causes and repeating this process, we can identify the root cause. So let's do this to find the root cause. Let us ask, why are BFD and routing sessions flapping? The direct cause is this. BFD packets are intermittently delayed or dropped. Then we ask, why are BFD packets intermittently delayed or dropped? The direct cause is the system instability. Then we ask, why is the system unstable? There are 2 direct causes here. The first cause is high data traffic load leads the system unstable. Here, the system is the WAN router. The second cause is the BFD and routing flapping in turn makes the system even more unstable. In one word, high data traffic load triggers BFD and routing flapping, which triggers a feedback loop. So then we ask, why is there high traffic load on this WAN router? The direct cause is simple. All traffic is being forced through the single WAN router. So then we ask, why is all traffic are being forced through a single WAN router? The cause is this WAN router serves as both a single point of failure and a single point of congestion. So then we ask, why do single points of failure and congestion occur? The cause is there are flaws in the network design. At this point, we have identified the root cause. It is a network design issue. Now we can clearly see why these BFD and routing sessions are flapping. All traffic is forced through a single WAN router. It becomes both a single point of failure and a single point of congestion. This is not a configuration problem. This is a network design problem. This design flaw makes the WAN router highly prone to traffic overload. When the load reaches a critical point, for example, exceeding 70% of capacity, the CPU spikes. Interface queues and buffers become congested. As a result, BFD keep-alive packets are intermittently delayed or dropped entirely. This causes the BFD and routing sessions to flap. And here is the critical part. That flapping makes the WAN router even more unstable, which spikes the CPU further, which drops more BFD packets, which causes even more flapping. This is a self-reinforcing feedback loop.
Now we know what causes the problem. The next step is how to fix it. The solution has two parts. The first part is to suppress the flapping and break the feedback loop. We do this by tuning the BFD timers to make the BFD not too aggressive and not too sensitive to packet delay or packet loss. This method can immediately calm down the flapping and stabilize the system. But this is only a temporary relief. The second part is to fix the design problem. We can use the second router to establish another connection between the two sites. This removes the single point of failure and the single point of congestion. To distribute the traffic load across the two WAN routers, we can use ECMP or PBR or using AAR if we are using SD-WAN. This is architecture fix. It is root cause fix.
In this episode, we shifted our mindset from traditional engineer to network architect to solve the mystery of network flapping. This is what I call architecture troubleshooting. As we have seen today, when traditional troubleshooting reaches its limit, architecture troubleshooting provides the answer. By looking at the design logic and asking what and why. In the next video, I will apply this same methodology to solve another common but complex problem: voice quality issues. If you have questions about this case study, please leave your comments below. Do not forget to click the like button and subscribe to stay updated with the series. Thank you for watching. I am Ray. I will see you in the next video.